Good afternoon. I'm Francesca Nestor, Assistant Professor in Politics and Government, and co-director of the COVID-19 course along with Dr. Kira Bailey in Psychology and Neuroscience. It is my pleasure to welcome you to the 18th lecture in our series. Today, we will learn from Dr. Suren Ambegaokar. Dr. Suren Ambegaokar is an Associate Professor in the Department of Botany and Microbiology at Ohio Wesleyan and is a David O. Robbins Professor of Neuroscience. He is currently the Director of OWU's Neuroscience Program. A native of Southern California, Dr. Ambegaokar graduated from UC Berkeley with a double major in molecular and cell biology and film studies. He completed his PhD in neuroscience at UCLA and completed his first postdoctoral position at the University of Texas Medical Branch, where his research focused on human genetics and fruit fly models of Alzheimer's disease and related diseases. Dr. Ambegaokar then completed an NIH fellowship in neurovirology at the University of Pennsylvania, studying HIV infection in the brain. Dr. Ambegaukar's current research uses fruit flies and cell cultures to study genes related to Alzheimer's disease, as well as the immune response to viral infection and how RNA regulation is altered in both of these diseases. He teaches courses in genomics, neuroscience, mycology, virology, and will be teaching a seminar in the fall on coronaviruses. As a reminder, you can use the chat function to ask questions throughout the presentation. I will select questions for Dr. Ambegaokar to answer if time permits. You can also continue your discussions on the COVID-19 course Facebook group. And now, when will it be safe to go out again? Challenges in vaccine development and why it may be okay without one.
There we go. Thank you so much, Francesca, for that introduction. And good afternoon, everyone who's joining in right now. I'm very excited to be here and to be part of this series. And I want to thank Lori Anderson and Ashley Beiser for the ones who kind of first came up with this course idea and kind of wrangle the faculty together to participate. And also give my thanks to Francesca Nestor and Kira Bailey, who've been really running the course, managing it, and making sure it runs smoothly for everyone, participants and as faculty as well. I know it's a big job, so I really appreciate all the work that they've been doing. So I'll just get into it then. So the title of my talk is When Will It Be Safe to Go Out Again? Which is, of course, the 10 billion, trillion, gazillion dollar question there is right now. And I can give you the answer, which is we don't know. So I apologize if the title was a bit misleading or false advertisement. What I wanted to do with the title was really just more provoke the question about this idea that we're going to get a vaccine pretty soon, and that as long as we kind of hold out for maybe 6 months, maybe a year, then we'll be fine. The vaccine's in, and the pandemic is over, and we're back to normal. And I think what gets lost in the discussions, or when we talk about it that way, is that that we've kind of, I think, taken for granted how hard it is to actually make a vaccine or any real drug. And that's because I think we kind of take vaccines for granted. We have so many of them that work really, really well. And so I thought it'd be a good idea to just kind of go through that process a little bit. And so this talk isn't really about how vaccines work or how your immune system works. It's more about the kind of practical steps that are needed to ensure safety and effectiveness of a vaccine and to actually get it out to people. I'm happy to give another talk if people are interested about how vaccines work and what a herd immunity is, or antibodies and antibody tests, and all that kind of stuff. And I was hoping to get to some of that in this talk, but it was just going to be a little bit too much to fit in for the 45 minutes, 50 minutes we have here. But what I wanted to do really was to kind of like reset expectations in people's minds of when a vaccine will likely be available to most people. And hopefully with that in mind, think about then what we can do now without a vaccine, and plan for our lives without a vaccine in the near future. Okay. So my talk's basically broken into 3 parts. I'm going to first talk briefly about vaccines, but really focus more again on the practical limitations, or what I would call bottlenecks in getting a vaccine out. And you may be surprised to see how long a typical vaccine would be projected to make. And hopefully, again, that resetting your expectations about vaccine timelines. Then I'm going to be talking about those several new ideas that have never been tested before SARS-CoV-2. And I'm a virologist, so I like to refer to the virus as SARS-CoV-2 and the illness as COVID. And so some of the new things that are being done are vaccine design. There's actually a lot more things that are doing that's not just about vaccine design. It has to do more with kind of policies or regulation, which I think will tie into what we talked about on Monday. And then finally, I'll talk a little bit about how virus or contagion can be managed without a vaccine. Because again, I think we need to plan more based on what we have available to us now, rather than whenever a vaccine may be available. So before I go into all those details, I just want to kind of take a step back and just review really quickly what a vaccine does and why everyone is anxious to have one for SARS-CoV-2. So I have a very simplistic schematic here of what a vaccine does. On the top, we can imagine we have some healthy person here, and they encounter a bad virus, a really harmful virus. And in those cases, that person will become very ill from the infection. The severity of the illness or the length of the illness may vary from person to person, but for most viral infections, we're looking at a couple of weeks for the true infection, but then there could be some lingering effects after the infection. And what we hope to happen is that the person then is able to recover from the illness and hopefully essentially back to the full health they were before. All right, but you'll see I have a question mark here because we don't know if that will happen. And especially for a virus as harmful as SARS-CoV-2, it's unclear how well a person can fully recover. We know that there are lots of lasting damage to several organs, even if they do survive. And of course, the worst outcome is that a person does not survive, that they actually die from the infection. But the idea of someone being vaccinated then is that the same person that's healthy, if they were vaccinated before they ever encounter that same virus, before the initial infection, then when they're exposed to the virus for the first time, they essentially skip over this illness step. And ideally, the person would have no symptoms at all, and they may not even know that they were even exposed to the virus. But perhaps they may have some mild symptoms. You can see this person on the right, they're smiling, not as happy as they were before, so they're not as happy, but they're still relatively healthy, or have some mild symptoms, and they last only for a few days versus for weeks. And usually just some over-the-counter medications are sufficient to have the person be able to recover. So that's the idea of vaccination. But also importantly, what's great about vaccines is that they just don't protect the person who's vaccinated, but also limits the spread or the ability for the person to spread it to others. And especially others who may be more likely to become infected or who may be likely to die if they are infected. So it's a great thing is that they don't just protect the person, the individual person being vaccinated, but they help others in the community who also may be sick or not as well. But I do think it's important when I say this is that it's also good to keep in mind that there's no vaccine that is 100% effective. And by that, I mean that a vaccine is not a guarantee that you won't be infected. A vaccine just reduces the odds of you becoming infected, reduces the probability. But that being said, on the right here, you see a graph of several common vaccines we give, mainly to children, at least in the US, and the effectiveness rate in the middle. I know the numbers are kind of small, but essentially the majority of these are over 90% effective, which is a really, really strong reduction in probability for infection. And again, not only are not every vaccine is 100% effective, but also not everyone can get a vaccine. For those who have some immune suppression or other illnesses, they may not be able to get a vaccine. And that's why it's even more important for those that can get a vaccine to do so to help protect those who can't get a vaccine. Okay, so going then kind of briefly into some of the kind of practical barriers into making a vaccine. So I've kind of come up with what I think are 4 major bottlenecks that I wanted to bring up. And we could probably talk about more or kind of break it down into other smaller barriers, but I think this is a good way to kind of take a larger view of things We can just start with 4 major bottlenecks. So the first bottleneck I would call as finding something to make something testable. And what I mean by that is coming up with something that we actually can put into a vial and then test in animals or test in humans. And so what I'm showing here in this diagram on the left is the kind of traditional method of making vaccines. And I say traditional, but this is really the tried and true method. These are all the vaccines I showed you on the last slide were all made with this kind of method, or some kind of variation of that method. So the whole process, it can be complicated. And like I said, I'm not going to go into all the different details, but I think we can basically boil it down to 3 simple steps. The first step is to isolate the pathogen, the really harmful pathogen, from a patient or from the environment. Okay. The second step then is to grow up a lot of that virus in a dish, in a lab, in cell cultures. Maybe you need some animals to grow up the virus. But the idea is we actually need a large stock supply of the harmful virus, because what we want to do then is to alter the virus. We take the harmful virus and we alter it. And that's the third step, and is to take the harmful virus and make it not dangerous. And that's, there's essentially three different ways you can do that, as shown in kind of the middle of the diagram here. And again, I'm not going to go into the details, but essentially they boil down to either killing the virus outright so it can't replicate if it gets into a cell, or keeping it alive so that it does replicate, but we allow either natural selection or we target specific mutations in the virus to essentially make it a toothless virus, a virus that can't cause any illness. And so those are kind of the 2 most common ways to make a vaccine. And a third way is to not even worry about having a full virus. You just take parts of the virus. You just take, maybe in this diagram here, we just take some of the proteins that are on the outside of the virus and just use those proteins inside the vaccine. Okay, so whatever method you use, though, the idea is that one of these things goes into a vial and then we test it. That's what we test now in animals and in humans. Okay, so this is the first bottleneck because each of these steps can take a long time. It can take months to years for each one of these steps to make, especially the last step, to make it non-harmful. That probably takes the most amount of time. So this process here can take years, can take 1 to 5 years just to get this bottleneck, go over this bottleneck. So then the next bottleneck has to do then is what we call preclinical testing. And so just to kind of give you some the nomenclature here. So anytime you hear the word clinical, that means humans. So clinical is humans. So if it's preclinical, it means before we're getting it to humans. And so usually that means we're doing it in animals, sometimes in cell cultures as well. So when we start to actually test a vaccine or any drug or any therapeutic, this is true for any drug or therapeutic, there's always 2 outcomes that we're trying to measure at every single step. And that's safety and that's efficacy. Those are the 2 outcomes we're always looking for. And how you measure those in each step can differ, but you're always looking for both in every single step of the process. So for safety, the biggest question is always going to be toxicity. And I think of it as being big toxicity and little toxicity. Big toxicity basically meaning, does it kill the animal? Does it kill, is it essentially a poison? Is the animal going to die due to whatever is in the vial? Is it a poison of some sort? Okay. So that's obviously a big question. That'd be the worst to happen. But there's also quote a little toxicity, meaning that even if the animal doesn't die, there may be severe damage to an organ or a tissue that would obviously be very harmful to the animal, perhaps later down the road. So for example, liver toxicity or kidney toxicity, those are very common types of organ damage that can occur from a drug or a therapeutic. And when we're dealing with something like a vaccine that affects the immune system, that can then affect any organ system in your body, the heart, the brain, the lungs, all those can be affected. So there has to be then close inspection of all the organs. Even if the animal survives, there's close inspection of all the tissues to see how much, if there's any damage done to those organs. And then beyond just kind of the big toxicity aspects, we were looking for side effects. So these can be changes to physiology, like things that might affect heart rate or breathing rate, or perhaps behavioral changes. Maybe an animal stops eating as much, or maybe they don't mate as often as they should. So it could be these other kind of behavioral, physiological effects that are not outright toxic, but clearly can affect the quality of life, so to speak, going forward. And critically then, we also want to test different doses. And there's this old adage that everything is a poison at the right dose. Even water can be a poison if you have too much of it. So we always want to test what doses give you toxicity, and then try to or side effects, and titrate either up or down depending on where you are on the concentration. And so those are just a couple of ways you can look for safety. If we're looking now, the other outcome then is efficacy. And again, there's different ways you can always measure efficacy. For vaccines, the big question is it immunogenic enough? And that's just a fancy way of saying, does it actually do something to the immune system? Does it actually get the immune system to make the antibodies that it needs to target the virus, to stimulate the immune cells? So that's a big one. But again, there are some other subtle questions we can ask about efficacy, sometimes antibodies are made, but they actually don't work to clear the virus. They're not actually very good. It was a great example a couple of years ago. There was a vaccine candidate actually for another coronavirus, for SARS and MERS, that they got antibodies to be made in humans, but the antibodies weren't actually really good at clearing the infection out. So just because an antibody is made doesn't actually mean it's going to do what you want it to do. So that's something you want to test. And again, dosing. And this is where it gets interesting between safety and efficacy, because there's always there can be a push and pull between safety and efficacy, right? So you may get something very efficacious where you get lots of antibodies pumping up, it's doing what you want, but then you get lots of maybe liver damage or lung damage because of that. So you kind of have to find the right balance between what is as efficacious as you want it to be, but also doesn't cause any toxicity or safety or side effects. So there's always kind of a push and pull between safety and efficacy. Okay, again, so this is the bottleneck here is because, again, we can imagine trying to titrate, trying to get everything that be as safe as you want it to be and as efficacious as you want it to be. Again, this can take years. Again, it can take up to 5 years, if not longer, to get something that is efficacious. So we got something to test, now to actually make sure it's safe and efficacious, even before we get it into humans, can take several years in that process. Okay, so now then imagine we've passed the clinical trials, we have something that looks good in animals, it seems safe enough, it seems efficacious enough. Now we actually want to test it in humans to see if the humans react the same way. So this is what we start then in what we call clinical trials. And what we have here is a very stereotypical system in which human trials are conducted. And this is basically universally done, as far as I know. Every country uses the same paradigm to help compare results from one country to the other. And it's divided into 3 phases. And basic idea is you have to pass the one phase to get to the next phase. And the big reason for why we have so many phases is safety. Safety is always the #1 issue that's being looked at. And efficacy, all those other things are lower on the list. Safety is the #1 priority. And so by having these phases, this process minimizes the risk of getting something that could be dangerous to as few people as possible. And that's not to say it doesn't catch every risk. Sometimes things get through and we later on find out that they actually can be harmful to certain people or certain conditions, but it does a really good job overall in minimizing that risk. Okay. So what we have then here is the biggest difference between the phases, between 3 phases, is really just the number of people involved. We're basically asking the same questions in every single phase, but the number of people we're putting into the phase keeps growing as you go from 1 to 2 to 3. but we do ask a couple of different questions in each phase. And for phase 1, the biggest question is it toxic? We're looking really just to make sure it's safe enough to go forward, that there's no major side effects, no major toxicity in people. And so we're just looking at a few dozen people, really, and most of these people are going to be healthy. They're not really any patients or people that are affected by the disease. And you can maybe look for some efficacy, but really you don't have the numbers to really determine that as well. You're just looking to see, is it safe enough to go forward with the next phase? Okay. So phase 2 is really the kind of, if the drug or the vaccine passes phase 1, goes to phase 2, and now we have a lot more people involved. We have usually in the hundreds of people involved, and now we have enough numbers to actually look at efficacy, to see, are we getting what we call the endpoint that we want? Are we getting enough antibodies made that we want for the vaccine? We're still always looking for safety. That's always going to be in every phase. But we also may be looking for more side effects, more subtle side effects now that we have more people in the trial. Okay, and in this case here, we're actually using real patients. If this was a drug that we had a disease for vaccines, we wouldn't actually test people that were infected. But if this was a drug for another disease, we would test real patients and non-affected persons as well. And so you have a randomized controlled trial in these groups here. Okay. So because in phase 2, we have this increased stringency of looking for efficacy with safety, this is where most drug candidates and most vaccines fail phase 2. So a lot of them get through phase 1, but phase 2 is where most drug candidates will die. And if it can get through phase 2, okay, then we can get to phase 3, where we have the largest number of participants, and here we have in the thousands, perhaps even tens of thousands in phase 3. And again, we're still looking for safety, looking for side effects, and we want to make sure it's still as effective as expected before. Now that we have a much larger population, hopefully we've accounted for more variances, but I'll say that most clinical trials, as we're talking about previously in the course, we're talking about inequities between racial differences and sex differences, gender differences. This is in true clinical trials, and the way they're constructed now, don't really take those into account. So once they get passed through phase 3 and into everyone else, that's when those things will often be determined, which is not a great system, but that's how it is right now. So this infographic here, I think, does a nice job showing kind of the percentage of failure of drug candidates at each round. And I know the gray is kind of hard to see, so I'll say the numbers, what they have here. But we have phase 1, phase 2, and phase 3. And you can see there's a cutting off, a culling of candidates at each phase. And so from phase 1, only about, I'll say phase 1, about 40% of drug candidates fail phase 1. So about 60% of candidates will make it past phase 1 to get to phase 2. And phase 2, about 70% of candidates fail phase 2. Okay, so that's a big number, and I mentioned before that's where we see the biggest loss, because we're looking for increased stringency of safety and efficacy. Then those that go on to phase 3, still about half of those that go to phase 3 will also fail. And then finally, there's a last little step here where all that data that was collected from the phases goes to the FDA for final review, and they make sure that the trials are done correctly, that there's no errors, there wasn't any fudging of data, and if there is something that they catch that's a little bit awry, they won't approve it. So there's still about 15% of candidates that go through all the phases but don't get approved by the FDA. And you can see here, I also have the timeline for approximately at least the trials more likely to be on the longer end of things, if not longer than what I have shown here. Okay. So in the end, of all the vaccine candidates or drug candidates that go through, we have less than 10% of therapeutic candidates are actually approved for general use. And I mean, just think of that. That's with all the preclinical trial stuff we do with animals, all the years it took to get preclinical trial data, and then to get through phase 1, and then to get phase 2, and then to get phase 3. After all that, only about 10%, 1 out of 10 drug candidates will actually be approved to meet safety and efficacy standards. And again, the Bottleneck. So if you add up all the months and years I have here, you can do the math that this can take years. Just going through the clinical trial process can take years to get finally approved by the FDA. And then the final bottleneck that I'll put out for this for us to talk about is manufacturing. Okay, so this process is a little bit different for vaccines than for typical drug therapeutics, but overall it's pretty much the same process. But so finally we have, imagine we have a drug that's FDA approved, it's licensed vaccine, so go ahead, let's give it to people, right? But this actually requires then us to manufacture millions or billions of doses of individual, sterile, equally effective vials for every single person, and each of those have to be routinely tested for quality control. And you may think that this actually shouldn't be too hard, especially if you're comparing a vaccine to other types of drugs, let's say something like another antibiotic or other kind of medications, which are basically just small molecules that you can synthesize with organic chemistry. Vaccines are not that. Vaccines are complex, complicated mixture of biological components, and it's not just something that you can, organic chemists can synthesize on their bench. Requires highly specialized facilities, and most factories basically just make one type of vaccine. That's how specialized they are. So for the polio, let's say a polio vaccine, there's one factory and all its job is to make just the polio vaccine. And that's not true for lots of other pharmaceutical companies where they can generate lots of different drugs in the same facility. And of course, we're looking at things that have to be completely sterile. So you see this person here is totally suited up to make sure that they're totally sterile at every step of the way. And again, routine quality control to make sure that there's nothing dangerous that gets into the vaccine if it's given to a person. So this process of actually building factories and getting doses out, again, can take up to 5 years just to make a facility and to get the doses out in the quantity that we want to deliver to people, right? So it can take years. So if you've been following along and you kind of do the math of adding all the 4 bottlenecks together, and this is kind of nicely done in this article here, which is one of the assigned articles I gave for the class. If you add up all the kind of the bottleneck here for looking for something testable, preclinical trial testing, all the clinical trials in phase 1, phase 2, building a factory once it's approved, making the actual doses and regulatory approval, we're looking at a timeline of a vaccine being ready by 2036, right? And that's a pretty optimistic timeline for something that would be totally streamlined, that we're assuming that there's no problem, that we have a candidate that makes it through everything without any problem. We go from one to the next. But so we're looking at about 16 years is what would be, actually a pretty decent approximation or estimate for a vaccine if we were starting now and to get starting from scratch. So let me just let you sit with that for a bit. So that's hopefully is resetting our expectations about timelines for vaccines. We're looking at, years, perhaps even decades to go out for something that most people would predict would take that long. So, but if you've been following along, of course, with the media, and even just yesterday, Dr. Fauci testified to Congress that he's cautiously optimistic that we're going to have a vaccine ready, maybe even as early as the end of this year, right? So how do we get them from a 16-year timeline to something in 6 to 8 months? Where's the change going to happen for that? So for SARS-CoV-2, there's many things being done differently than the kind of traditional way that we approach vaccines, and that the goal really is to speed up the timeline. And I'm not going to discuss all of them, but I'll summarize a few of the major ones that I think have the biggest effects in shifting down or shortening this timeline. Okay, so right off the back, all the work that was done to find something testable, that first bottleneck I talked about, was done super quickly. And that actually came because we were fortunate, quote unquote, fortunate, the fact that the virus actually was very close to SARS-1, SARS-CoV-1 back in 2002. So a lot of what we're basing our current vaccines are based on our knowledge of SARS-CoV-1. We actually don't know a lot about SARS-CoV-2, but it's because it's so similar to SARS-CoV-1 that we're using some of that data, that knowledge to assume that SARS-CoV-2 is very similar. So the academic research, that's basically, we're skipping over that. And we're essentially skipping over all the preclinical trial data. We're basically skipping testing animals and going straight into humans. We're doing some cell culture work, but we're not doing really any animal testing. And then if you look at the clinical trials, normally we do it kind of sequentially, but now we're kind of overlapping them. So that's not strictly on top of the other, but we're giving very short intervals between phase 1 to phase 2 to phase 3, meaning that we're setting up phase 3 trials now, even if we don't know the results for phase 1. So that requires recruiting more people in, paying all the people that we need to do to run the clinical trials, even though we may not even actually use those people for those trials. And also then we're using the FDA approval. Of course, normally would take 6 months to a year for approval, but of course that's now top of the list. Whenever something comes in right away, that's going to be reviewed. So if you, if you put all that together, that's how we can essentially cut off that timeline in half, where we now get it down to about 2028 is where we can expect a timeline if we just use these levers to change some of that stuff. Of course, the big risk in doing all this stuff is safety. We're compromising, we're assuming a lot of risk and safety in order to speed up the process. And we're hoping that the safety is going to be safe, but that's a chance, that's a risk we're taking with this. Okay. So there's two other main ideas that I think are going to be the biggest risks that we're taking, but also will have the biggest rewards in the end. Because what we had before is that's 2028, but how do we shave off the 7 years we're thinking about to get it to next year? How do we get closer to that? So the first biggest risk then is using a totally different method to make a vaccine. So instead of using the kind of traditional method I described before, we're using essentially genetic engineering techniques to make what we can call genetic vaccines. And again, I'm not going to go into the details about that. Again, this article that I've highlighted here that I stole these images from does a good job describing that. And I'm happy to answer questions if there are later on. But I just want to kind of mention what those vaccines are. So we have 3 different kinds of genetic vaccines. We have a DNA vaccine, an RNA vaccine, and what's called a viral vector vaccine. And the biggest difference between the genetic vaccines and traditional methods is that it's way quicker. It's much, much quicker to make these than traditional methods. It basically needs only weeks, maybe even days, to get one of these in a testable format versus the months to years it would take for a traditional vaccine. So it's much, much quicker. But the risk is that no vaccine has been approved using one of these methods. So again, we're taking a risk in terms of both safety and efficacy. We don't know if it's actually going to work in humans. The DNA vaccines have been tested and haven't been shown to be effective as of yet. Viral vaccines have come the closest. There's an Ebola vaccine that uses a viral vector. And it's done pretty well, but it hasn't gone through the full test yet, the full phase 3 trials. Right now, and an RNA vaccine has never been tested. It's being tested right now for COVID. So the vaccine candidate that has the most potential right now is an RNA vaccine to get that out, by end of this year or early next year. So yes, that's the biggest risk, but it has the largest reward because of how quickly it can be made. And then the second biggest risk reward is to start to build factories now and start to make vials of vaccines now, even though we have no idea if they're safe or effective. So you can think about this as basically you're putting millions, if not billions of dollars into building factories and producing something that may just get thrown away, that may never be used. So this is a huge risk to companies to put all that investment in and not have any way to recoup any of that money back. And so to kind of help that along, to help incentivize companies to put that risk in, some nonprofits like the Gates Foundation is putting up money to say, we'll cover the losses for some of these efforts to do this parallel processing of manufacturing and clinical testing. And the Gates Foundation has committed up to supporting up to 7 candidate vaccines, essentially covering those losses, which could be up to at least would be millions or hundreds of millions and potentially even billions of dollars to get one vaccine that would work. And there's no guarantee that these will work. This is just still trying these out. Okay. So if you put all that together, all those things together, that's how we get, the building the factory simultaneously with a genetic vaccine shaves the timeline from 2028 down to 2021. So that's where we get this estimate of getting a vaccine ready by the end of the year. So, but I hope you can appreciate how many things have to go right for this to happen, and why most people who kind of, who know about vaccines and immunology are pretty dubious about this timeline actually being met. Is it possible? Yes, it's possible. Is it probable? No, I would say it's not probable. But everyone's optimistic. Everyone's still hopeful it can happen, and no one's trying to be a downer about things. But it seems the odds are against this from being this quick. But it'd be great if it did. So one other idea I wanted to also mention that also could speed up some of the trials is this idea of a human challenge study. And this has not been approved yet to be run, but it's a very interesting idea, and I wanted to bring it up. And for those of you that are going to join us for the discussions on tomorrow and Friday, the Meet the Prof sessions, it's one of the kind of discussion points I brought up. The idea is to intentionally infect healthy people who have been given a trial vaccine. And the way this works, or why this is better, is because you need a lot fewer people and you can get the results a lot more quickly. But of course, it's ethically wrought. The idea to actually infect people, knowingly infect them with something that may not work, and with the vaccine that may not work, and have them succumb or have all the illness, potentially die from it, is not really the standard way we test anything. So to do this, it would be a very dramatic departure from how we typically test things. But it could be, again, high risk, but potentially high reward from this. So before I go into the last part of my talk, I did want to mention 2 other things I think it's worth mentioning when we talk about developing vaccines for COVID. Is that we're focusing on COVID because that's obviously, it's a big issue, it's a huge issue, but we can't forget that there are still other vaccines that are life-saving that also still need to be produced right now at the same time that we are going to make a COVID vaccine as well. So like for polio and measles and mumps, these are real issues in many parts of the world still. And actually, we've already seen cases of these diseases increasing because they have not been able to get access to the vaccine because of COVID. They're not able to go to the clinics and get vaccinated. And so cases of polio and measles are rising in many parts of the world. And so these also have to be produced at the same time we make the billions of doses of COVID vaccine that come along. And that has been quoted essentially as being an undertaking almost unimaginable in scope, in the sense that all the biopharma companies are aware of this problem and they're discussing solutions for this, but no real solution has been yet determined of how we can, the scale of manufacturing that's needed for all of these to process, how are they going to do it? So they're trying to work with governments and other groups to try to think about how to do this, but this is still a major issue. And also, I think it's important to realize that all the clinical trials I talked about that require thousands or at least hundreds of people, you know, there's a finite number of people at some point that are used in clinical trials. And there were clinical trials that are being done for lots of other diseases, including things like cancer or other vaccines for, like, let's say for Zika. And so people that were being used, that were kind of designated for those clinical trials, are now being shunted for COVID trials. And so all those trials we had for things for new cancer drugs are now being postponed, and potentially indefinitely, until some new source of funding or some new way to promote that comes along. And so I'm not saying that this is necessarily a bad thing. I'm just saying that we have to realize that we're making a sacrifice, we're making a compromise in what we're choosing to put our resources into. Okay. All right, so the last few minutes I have here, I'll talk about a little bit about things about what we can do from now. So I hope that the last part of my talk helped to reconceptualize the idea of when a vaccine will be ready, which my opinion is that realistically we're looking at years, not months, but that's just my opinion. And so with that in mind, what can we rely on? How can we try to think about getting back to something more normal without a vaccine, without a true vaccine? So our options are limited. I want to make sure that's clear. Vaccine really is the best option we have, but that doesn't mean we can't do things to kind of keep things better under control. And if they work, if we get it to work really well, they actually can work almost as good as a vaccine if they're done correctly and if we're really engaged in that process. Okay. So I'm just going to mention two ways that I think a contagion or a virus can be managed without a vaccine. And so what I say by manage, we're not eradicating it, but it could allow for a relatively safe return to interactions. So the first one is pretty simple. It is testing. I'm not sure how more emphatic I can be by saying testing. It is the thing we need to do, testing. And what I mean by testing is kind of this massive, we'll call it either community or universal testing, along with some form of contact tracing. And it's important because the biggest issue with SARS-CoV-2 is that a lot of the spread, and this has been debated in terms of the actual number, but it's clear that a good percentage of the spread is through asymptomatic or pre-symptomatic spread. So people who don't even realize that they're sick or showing symptoms are then spreading it to other people who then will become sick. So in order to kind of to track that, to know who those people are, we need to test people who especially those who don't show symptoms. So who we're testing now are people basically that show up to clinics or who are self-volunteering to be tested. But we need to kind of have a door-to-door campaign, quote unquote door-to-door, where we're testing as many people as possible, even those that don't show symptoms, especially those that don't show symptoms. So we have a kind of a baseline measurement of how much virus is actually in our communities. And this universally, every single health official will agree to this, that this has to be a central part of any plan to control the spread of the virus. And of course, that's not worth mentioning really, but of course, maintaining basic safety measures of physical distancing and wearing masks. That's the bare minimum we can do. But that's the testing is really a strategy to go forward. The reason I mention this is because we know that testing actually works to curb the spread. And I hope we all know here that the US is the worst, is the country that's dealing the worst with this pandemic. And by all measurements, we are the worst country that's handling this infection or this pandemic. Brazil is getting pretty close, but right now US is still the worst of all the countries. Almost all the countries are able to are bringing the curve down. The US is still hovering pretty high up on the curve. And there's different reasons for why different countries are doing it better, and so it's hard to compare one to the other. But I wanted to at least mention these three here because I think at least especially South Korea and China I think are the most comparable to the US because they had very high rates of infection like the US, but they had a strategy, that a campaign to actually, they had investment by the government and cooperation by their citizens to engage in something that was effective to bring the curve down. And Singapore was pretty good for a while. They had a sharp increase recently, but they instituted testing and they're bringing the curve sharp. Their numbers are going down very swiftly. And it's basically through testing. So it's not a hard thing. It's not a hard concept. You just test it and trace it, and you can bring the numbers down. Okay. And I also want to mention that for the US, we are nowhere near where we need to be in terms of testing. The record we had for testing was about 500,000 tests per day. We need to be in the millions of tests per day. And so we're way behind in all regards: testing, contact tracers, people who actually can go out and do the tracing, and then a strategy for tracing, some kind of plan to actually do this effectively. And so why are we so behind? I mean, the answer is pretty simple. The government has failed its responsibility to do this, and in such a way that this, just about a week ago, this editorial came out, which is a pretty scathing rebuke of both the US and the UK's policy to the pandemic, published in Nature Biotechnology. And so I know it's easy to say, a lot of people will be saying, oh, government failure, but for a science journal to call out the government on its policies, that's bad. That means something bad has happened with the government policies. And in a lot of the reading I've been doing so far, it seems to be pretty clear that our administration doesn't really want to have a national strategy for massive testing. I don't know why. It's trying to have states rely on testing instead of having a national strategy. You want states to pay for things on their own. But that's literally what the administration has decided to do, is to not have a national strategy. So all states are left on their own. All of us are kind of left on our own to kind of figure something out. Given though that I do take pride in a lot of my fellow Americans here, that we can respond to some action, and a lot of nonprofits and academic institutions and even a lot of private sector companies are trying to come together and try to come up with a strategy, due to the fact that the government hasn't given us a strategy. So for example, the Rockefeller Foundation is working to coordinate resources to try to have 30 million tests per week, which is a good number by the end of the summer. And to me, it just seems, it's just baffling to me why we're not doing this more, because this is the one thing we actually have control over, and that we can do now. We have all the research, we have the tests, we can make them really quickly. The tests are not complicated, and I'm just baffled why this has not been more promoted, just in all levels of government. So that's the biggest thing for sure. The second thing I'll just mention is that in terms of thinking about therapeutics, vaccines are, of course, the vaccine is the best thing, but we can also, a lot of people are actually more encouraged that antivirals might come online sooner than a vaccine. And so I like to think about this kind of like an offense and defense on a sports team, or maybe in a military camp metaphor. So to me, a vaccine is like your defense. It protects you from being infected in the first place. That's what really want to have to happen. But an antiviral is a good offense. So it attacks the virus. If the virus gets into your body, you've been infected, it will attack it. So an antiviral is strictly analogous to an antibiotic. So an antibiotic will fight bacteria. An antiviral fights a virus once you're infected with it. And so people are more excited or more optimistic about antivirals because, one, they're a lot easier to manufacture. So these are the small molecules that an organic chemist can make on their bench. They're actually much more simpler to make than a vaccine. So you can make them more easily and more quickly. There are all sorts of ways we can tackle the virus or the infection. You can either tackle the illness itself, so we try to reduce the severity of COVID, the length of COVID, or even perhaps reduce the ability for someone to shed the virus. Maybe they're infected, but maybe they're reduce the ability for them to pass it on to others. And in some cases, if you have a drug that's really good, potentially you could even use it prophylactically to take it before you're infected to prevent you from being infected. So this is kind of taking a page a little bit from the HIV playbook a little bit. Since there is no HIV vaccine right now, there have been recommendations to take antiretrovirals before, if you're a high risk in a high risk group, to get HIV to prevent transmission, and that's been shown to be pretty effective for preventing transmission of HIV. So it's not what you want. It's not the best solution. Vaccine's still better, but if it's a good antiviral, it could kind of work like a quote unquote daily vaccine that you would take daily or weekly or something like that. And what's great about also antiviral therapeutics is that we can use a lot of existing drugs already that have already been approved for safety, so we can get these out much more quickly. We don't have to go through all the phase 1, maybe even phase 2. We can kind of jump through phase 2 to phase 3 to test some of these drugs. So this was just reported last week. This is the first drug to really show clinically that can reduce mortality in COVID patients by about 30%, which is huge for given what we're dealing with now. And this is a cheap steroid that just reduces inflammation. And it's so people have been really excited about this. But this is just one thing. There's many other things we could still come along that could tackle the virus earlier in infection that would be even more helpful to more people. All right, so I'll just then leave you with a couple of concluding remarks. So I want to say, of course, that a vaccine is going to be the safest and most reliable way to reduce infections. And if we get a good one, and that's a good campaign, we could even eradicate SARS-CoV-2. But the realities of vaccine development is that it's going to probably take a couple of years to get a vaccine that's safe and effective, and then also available to the majority of the world, not just in certain populations or certain countries. But without a vaccine available, there are approaches to managing the spread of the virus, including increasing PCR tests for the vast majority of the people, using contact tracing, and perhaps antivirals that may come on sooner. And I think it's important to think about this in a more practical way, but still optimistic way, is that the way things are currently in our country, SARS-CoV-2 will likely become endemic, meaning that it's going to be around. Like we're not going to get rid of it anytime soon. So we need to then think about public policies with this in mind, rather than relying on uncoordinated efforts or underfunded efforts to tackle this. We need to have a real policy in place to deal with this. So I will end it there, and I'll thank you all for your time, and I'll take any questions as they come along.
Thank you. That's such a wealth of information, and I think was really helpful to a lot of us who don't have your expertise, that have been hearing details of this thrown around in normal conversation and not knowing how to follow it. It was very insightful and helped me a lot. We've had an excellent conversation going on in the chat, people discussing different factual pieces of information, sharing their knowledge of past epidemics. I have questions that are sort of nuts and bolts, and then there are questions that are more like big picture and what can we do in future oriented. So I'm going to try to get to as many as I can. Of course, if we can't, well, then we have the Meet the Prof sessions to look forward to.
Right.
One question is, who are these people, the people who are participating in the clinical trials and taking the risk? Who's in this pool of people? How do they get there, and how risky to them is it, and how is that managed?
That's a really good question, and I've thought the same thing, and I'm still actually not certain of the details. I know there are dedicated companies or different groups that manage clinical trials. That's their specialty, is to manage clinical trials for lots of different groups. And so I think what they're trying to do is, again, recruit people who may be affected, or might be higher affected patients in a certain group, and then trying to find people who are the control subjects as well. And there is I believe, and I don't hope I'm not saying this incorrectly, but I believe there's some kind of compensation involved for some of that risk. Nothing to hopefully, the idea is, though, we don't want to exploit people just by paying them money, but there are a lot of things are volunteer basis for those who are a control group. So I think there are these companies that specialize in clinical trials. They go out and try to recruit from the population at large. And that's a great question. And I don't know. The short answer is I don't know, but I will find out soon because I'm also curious about that.
And we also had a few different people asking about this idea of herd immunity. How does that fit in with all of these different pieces, whether you're talking if we have a vaccine, if we don't have a vaccine, where does herd immunity that we've heard so much about come in?
Yeah, then that's a great question, and I was going to try to fit that into the talk today, but it just was a little bit extra. So herd immunity, there's two ways to think about it. So people have been speculating that, well, because the virus is just kind of everywhere, that we're all going to get infected at some point, and if we're all infected and we all survive, that means then we have now immunity. We have the antibodies against the virus, so that way we won't be reinfected by the virus, and then we're going to stop the spread of it. And so that is true if, though, it assumes two things. It assumes that most people will survive the infection, and that the infection is not going to cause a lot of problems for people, and it requires a large percentage of the people being infected and surviving. And the estimates are about 60 to 80% of the population has to have been infected and survived to generate that. And right now, we don't have good numbers of how much of the population has been infected because the test for the antibody test, the serology tests, there's no real good one out there yet. So the numbers are just basic crude estimates, but the best guess is between 5 to 10% of the population has been affected so far, which is well below the 60% that we need. And even in New York, where it's the hardest hit, the best estimate is about 20% of the people in New York were infected. So it would still take years to get to some level of herd immunity. And you then, of course, are assuming all the risks of being infected and illness to get to the chance of getting herd immunity. And that's what vaccines are great, again, because vaccines provide herd immunity if enough of the population is vaccinated without that risk of illness. So vaccines also work with herd immunity, but herd immunity can be acquired without vaccines as well. So I hope I know it's a little confusing, but that clarifies things.
That's very helpful, but essentially it's telling us that what we've been hearing, in social media, this idea that if we just let it happen, it'll go really, really fast, and that's clearly not the case.
yeah, exactly. I mean, it's not been controlled so far, and it's still been a pretty low population that have been infected, and and I think the damage, the how many people will actually die if we let that happen is going to be exponentially more than we have now.
And then let's assume that we get a vaccine. It's been tested, it's being mass produced, it works. I'm wondering if what's the process for getting it out to people? How does that work? How will we find out where to go? How do we get it? Do we all get it quickly?
Yeah.
How does it happen?
That's a great question. I know a little bit, I can answer that a little bit. That's still also a little bit of a black box for me. I'm still trying to get some of that information. But the short answer is once a company has made a vaccine or has some vials ready, governments are going to come in and buy it and then distribute it to whoever they think is going to be needing it. So typically, almost universally, everyone knows that frontline workers are going to get it first. So people working in hospitals or in other clinics, they'll be getting that first, and that's going to be hopefully worldwide. They'll get that first. So even if it's made in February 2021, for us who are not frontline workers, for anyone who's not a frontline worker, it'll still may be another year or two before we actually get it, because all the doses are going to go to healthcare workers or ENT people, or people who are ENTs or that kind of profession. So the government-based, each individual governments are going to buy them, and then they distribute it to where they see fit, and then eventually after the frontline workers, it could go to your own individual health provider, and you can get it potentially from your health provider.
Now for a sort of what can we do question. We mentioned the fact that there's no HIV vaccine. However, advocacy and the efforts of activist groups working on making work happen in the government on getting treatments out and approved by the FDA and doing research, that worked and helped. What can we do as people living in the US to move this forward a bit, if anything?
Yeah, that's a great question, and I think it's great to have you on this conversation, Francesca, especially, and going off of what your talk on Monday, because I really do think this goes into thinking about political change, political will, more than just really just the science behind things. And I think I've been trying to think about that myself, because I'm trying to understand, why things like testing, like I hear a lot of people talking about vaccines, and I hear a few people talking about testing, but to me, it just seems so obvious and that this is the solution, and no politicians really talking about it. And I'm trying to figure out, well, what is the point? Why are people so hesitant to talk about it? And I know our president, was trying to say, oh, let's, the numbers make him look bad, but I know a lot of other politicians who are actually committed to, controlling this or trying to do something about it. And I'm not sure why they're not taking a more active role in this. So in terms of what to do, yeah, I would like to defer more to people who who are more involved in the policy side of things, and just in terms of talking about any kind of policy change you want to make, this would be one of those to get your politicians' attention. For advocacy groups, the idea for making a COVID advocacy group or testing advocacy group in the same ways that to fund for HIV, that's a great idea, because I think politicians are not really paying attention to this. But if enough people say this is what we want, I think there'll be something that could happen from that.
Well, this was wonderful. I could probably talk for another half hour, but right. We are at 5:01, so I'm going to wrap up. Thank you, Dr. Ambegaokar, for sharing your time and knowledge with us, and thank you to everyone who joined us and asked so many excellent questions. Don't forget that you can come to the Meet the Prof sessions for students Thursday at 4, for community members Friday at noon, and you should get an RSVP message about that. And thank you so much for joining us, and we will see you again soon.